So for the basic question, we're given a bunch of data from a study of women's bone health, and it gives us 38 women between the ages of 18 and 24 years and their daily intakes of calcium in milligrams. Alright, so part of our basic question asks us to display the data using a histogram and to describe the distribution of calcium intakes for these women. So this is what our histogram will look like. We get that from going to Stat, Edit, and putting in all our data there into L1, and then we would go to second stat plot, second y equals, and make sure that that plot is on, and that it's our histogram, and that it's L1. We then go to graph, and that's what we get as our histogram. Now it looks like there could be some outliers in there, so we could also make a stem plot, and this is what that would look like. And from that we get this histogram, and we can see there are definitely some outliers there. We can see that we have potential outliers at 1,933 and 2,433 milligrams, but to check that those are for like legit outliers, we would go to Stat and then go over to Calc and then do our 1-bar stats, and then from this we can get our Q1 and our Q3, and we use this formula, Q1 minus 1.5 times our interquartile range, plug in those values, and we get this and this, and we can see for sure that those outliers are legit. And from this we can determine that the distribution is skewed to the right and has two outliers at 2,433 and at 1,933. Part B of the basic question asks us to calculate the mean, the standard deviation, and the standard error. We do this by going to Stat Calc, going to our 1-bar stats, and we're given an X of about 926 milligrams and a standard deviation of about 427 milligrams. To find our standard error, we have the formula our standard deviation divided by our amount of women. So that's our 38. Our 427 divided by the square root of 38. That gives us 69.27 milligrams. This means that our true population mean is anywhere within a 69.27 milligram range above or below our mean of 926 milligrams. Alright, so part C of the basic question, we are asked to find a 95% confidence interval for the mean. So because it's asking for a confidence interval, we're gonna think pants. So our P, our parameter, is the women between 18 and 24 years of age, their daily intake of calcium. And our assumptions, we need to assume a simple random sample, assume independence, and we have an N of 38, which is greater than 30. And since it's skewed, but it's greater than 30, we can still continue or proceed with caution under the central limit theorem. Our name of our test is a confidence interval t-test, where we have the mean plus or minus t star times our standard deviation divided by the square root of n. So first, we don't know our value for the t star, so we would go to our table C in our textbook, and we need to know our degrees of freedom, which is our 38 minus 1 gives us 37, which we would round down to 30 in our textbook since 37 isn't a given value. And then that goes with our 95% confidence interval, and we get 2.042. That's what that says. So that gets plugged in, and so do our other values, our mean of 926 plus or minus our t star of 2.042 times 427, our standard deviation divided by our n, the square root of our n, 38, and that gives us 141.45. So from that, we would get our x plus or minus this value to give us this interval. So 226 plus 141.45, or no, that would be our minus, and then 226 plus our 141.45 to give us this. So our statement, we are 95% confident that our interval from 284.55 to 1067.45 milligrams displays the value of the daily calcium intakes of 18 to 24-year-old women. It displays the true value of these women. The fourth and final part of our basic question, we are asked to eliminate the two largest values and recompute the 95% confidence interval. And what do we notice from this? So we get rid of 2,433 and 1,933. Those were the outliers we found earlier. So we use our calculator to find the new mean, and these other values we'll need to complete the test again. So we do the same thing we did before, and we find that our mean is 856 milligrams, and then our standard deviation is 307 milligrams. Our new n of 36 from eliminating those two values, because of that, our degrees of freedom is going to be 35, 36 minus 1, 35, and our t star stays the same. So our new test that we're carrying out, when we plug that in, it's 856 plus or minus our t star 2.042 times 307 divided by 36 equals 104.48. So now our new confidence interval is 856 minus that value we just got, and 856 plus our 104.48 to give us 751.52 to 960.48. So from this we can determine that our outliers significantly impacted our data because our difference or our interval decreased from being at a value of about 283 to 209. So our new confidence interval statement, we are 95% confident that an interval from 751.52 to 960.48 milligrams shows the true value of women's daily calcium intakes. Looking at the advanced question, it says you play 2 games against the same opponent, and the probability you win the first game is 0.4. If you win the first game, the probability you also win the second is 0.2. And if you lose the first game, the probability you win the second is 0.3. Part A of the advanced question. So no, the 2 games are not independent. If you win the first game, the probability of winning the second game decreases. So essentially, if the first game, the outcome of the first game influences your outcome of the second game. Part B asks, what is the probability you lose both games? So our probability 0.6 times 0.7 gives us a 0.42 or 42% probability of losing both games. So we use this general multiplication rule to find this probability. We use that for part C too, but it basically says the probability of both of them occurring is equal to the probability of A times the probability of B given the outcome of A. And C asks, what is the probability you win both games? So you win both games. That's 0.4 times 0.2 gives us 0.08 or 8% probability of winning both games. Part D of the advanced question says, let random variable x be the number of games you win and to construct the probability model for x. So for 0, the probability you lose both games, that's what we calculated earlier, 0.42, and then this is the probability we win one game, and that could mean you win the first game at 0.4%, or not 4%, at 0.4, or 40%, or lose at 0.8, or that you lose the first game and win the second game at 0.6, and 0.3. So those multiplied gives us 0.18, those multiplied gives us 0.32, and we add those together to get 0.5. And then the probability you win both games, 0.4 times 0.2, is our 0.08. And this looks like this in our graph. And so we have a 42% probability, 50% probability, and 8% probability that you will win both games, that you will win one game, and that you will lose both games. Part E of the advanced question tells us to find the expected value and the standard deviation. So our expected value is our n, or how many times we win, times that probability. So, and then we add them all together to get 0.66. Deviation can then be found from putting our expected value into this. We have our n, how many times we've won, minus our expected value squared times that probability of winning that many times. So 0 minus 0.66 squared times the probability of 42% plus, and so on. And then we take the square root of that to get a standard deviation of 0.62. So the AB question gives us two different methods, A and B, of determining the level of contamination of E. coli bacteria used on each of 10 randomly selected specimens of a certain type of beef. They give us a chart with the data, and we're asked if there's a significant difference in the mean amount of E. coli bacteria detected by the two methods for this type of beef, and to provide statistical justification to support our reasoning. So what we're going to do is find the differences between A and B. So take A minus B. So like in our first trial or whatever, we're going to take 22.7 minus 23 to get negative 0.3, and so on. So we would take this minus this minus this, and so on to get those differences, and then we'll have 10 differences. We'll put these 10 differences in our calculator by going to Stat, Edit, and putting those in L1. And then we can go to our graph and hit zoom 9 if the format is funky, and this will be our distribution. We know we're going to use phantoms because it asks us to provide justification and stuff. So we start with our parameter, which is the levels of E. coli bacteria contamination in these beef specimens. And our hypothesis is whatever. Our null, or our HO, is mu of D is equal to 0, and our alternative, our HA, it's not equal to 0. And then this is our mean difference between method A and B. Our assumptions will assume independence and assume normality based off of the histogram we found here. We can see it's pretty symmetrical, pretty normal. You don't see any parent outliers. But because n is only 10, we only have 10 whatevers. It's not a large enough sample to proceed without caution. So we're going to proceed with caution. That was worded so bad, but we're going to proceed with caution because it's only 10. So we're going to get the mean and the standard deviation. So we go to StatCalc1 var stats and get our mean and standard deviation, all that good stuff. And we're going to do a paired t-test. We plug in what we found, our 0.29 minus 0 divided by our 0.629727 divided by our n of 10, the square root of 10. And that gives us a t of 1.46 and a p of 0.1793, and that's all considering our degrees of freedom are 10 minus 1 from the n minus 1 to 9, and our alpha of 0.05. Okay, so our p-value is 0.1793, and since that's greater than our alpha at 0.05, we will fail to reject the HO that it's equal to 0. So our statement is that we fail to reject the HO, that is our mu of D is equal to 0, because our p-value of 0.1793 is larger than our alpha of 0.05. There is not enough evidence to conclude that there is a difference in the mean amount of E. coli in the beef found by the two methods.